All right.
So our next speaker is Bastian Brandt. We talk about high precision spectrum of the flux tube and effective string description. So Bastian, the floor is yours.
Yeah, thanks a lot. And let me also take the opportunity for thanking the organizers for inviting me and giving this talk here. So I will be talking about a side project of mine since a few years by now, basically since my diploma, which is about the extraction of the spectrum of the QCD flux tube from lattice QCD with high precision, and then basically comparing to the predictions of the effective string theory and try to get something out from that. So I would like to first introduce the topic a bit. Well, I don't think I have to do much. We've heard a lot of talks about this already, so I will be extremely brief here. Then I will show a few results of myself in 3 dimensions, speak a bit about the prospects to do the same things in 4 dimensions, even though that's extremely hard. What has been found in 4 dimensions, however, are massive modes. So I will just show that very briefly on the world sheet, and I will also say a few words whether they might or might not be present in 3D as well. All right, so the basis of all this is, of course, the flux tube picture for confinement. We've heard talks about that already, so I will just consider static quarks for now. I will just neglect string breaking, so basically be working in pure Yang-Mills theory here. And in this case, if we now just start to pull the quarks apart, then the excitation spectrum will basically be dominated by these stringy type of excitations. And we can take as degrees of freedom the transverse oscillation modes of the string here, write down the low energy effective theory for these transverse oscillation modes, which then takes the form of an effective string theory. We can write down the associated effective action, and then all of the prefactors of all of the terms in this effective action will basically be constrained by the residual worldsheet Poincaré and rotational symmetry. Doing all this, we can then compute the associated open string energy levels, and the result can be written down like this. So at leading order, we have this full Nambu-Goto or light cone spectrum here, where we have one non-universal parameter, that's the string tension sigma here. Then on top of that, we have corrections to this. And the first correction originates from a boundary term in the action. It's a 1/r⁴ term with a non-universal boundary coefficient in front. And then we have an additional 1/r⁵ correction, which has a universal coefficient in front up to the string tension here. And then we will have higher order corrections. They start here at order 1/r⁶ if the next boundary coefficient is non-zero, and otherwise with order 1/r⁷. Actually, in 3 dimensions that I will mostly be considering, this term here is absent, so this is not there. Okay, so why am I interested in that? Well, apart from all the phenomenological aspects of this, I also became interested because, well, I thought it is also a good idea or a good opportunity to make contact to holographic duals for large N Yang-Mills theories. And in this picture, the confining string or the flux tube is nothing else than a 4D projection of the associated 10D superstring. So if we have suitable string backgrounds, and I'm absolutely not an expert for this, then one can compute the effective string theory action. And this has, for instance, been shown in these papers here. And then one sees that the non-universal parameters of the effective string theory are related to the bulk properties of the associated 10D string theory. So that means if we can compute these parameters, for instance, from the lattice, then this can provide constraints on possible holographic backgrounds for this duality. And I thought that would be a good way of making contact here. Okay, so what we want to do now is we want to extract the flux tube spectrum from lattice QCD. And I think I don't have to tell a lot about the methodology of the lattice. Also there we had talks about that already. So what we want to do is we want to, well, basically look at static quarks and forget about string breaking. So we are really looking at pure Yang-Mills theory. So then this fermion determinant that you typically had in QCD is absent. Now what we need to do is we need to write down suitable observables for static quark to, well, basically compute the spectrum of a static quark anti-quark pair. And one particular type of observables that we can use are Wilson loops, which are basically just these large rectangular loops on the lattice, where one direction is the temporal direction, the other is the spatial direction. Actually, these observables are just very good observables to extract the excited states, because we can actually put non-trivial operators on these spatial parts of the Wilson loop here, which basically just project onto given quantum number channels. So these Wilson loops are very ideal operators to extract the excited state. If one is interested in the ground state, then it's more advantageous to look at Polyakov loop correlators. So what is a Polyakov loop? A Polyakov loop is just a loop of flux winding once around the lattice in the temporal direction. And if we look at the correlators of those, then they are very good operators to directly look at the ground state. Okay, so if we want to extract the spectrum really with high accuracy, then we need extremely high precision. Okay, so that means just what we need to do is we need to use highly sophisticated algorithms. So we need to implement error reduction algorithms and use optimized operators and so on. And in this way, then we can really get the spectrum with a high accuracy. I don't want to go into the details, just telling that this is a highly non-trivial task, and then directly show you some results of what I got. So what I then set out to do was I was studying Yang-Mills theory in 3 dimensions for different values of the number of colors. So basically going from 2 to 6 with the idea of eventually going to the large N limit. And well, what I did was compute basically the static quark antiquark potential for different values of R. Then I fitted these results to the effective string theory prediction and extracted these non-universal parameters. And what I'm showing you here are the results for this non-universal boundary coefficient for different values of the lattice spacings and different values of N. Okay, so eventually, of course, we are interested in continuum results. So what we need to do is we need to do a continuum extrapolation, and the results are shown here. And now versus 1 over n squared. And now what we still need to do is this large N extrapolation, but this can be done, and this gives us eventually this black point up here. So this is the final result in the large N limit, and you see that there is quite a sophisticated error budget here, because well, we have to control all sorts of systematic effects here. So the first systematic effect that we need to control concerns the higher order correction terms in the effective string theory. Okay, so whether it's a 1 over R to the 6th term or a 1 over R to the 7th term. Since we don't know, we just have to look at the individual cases. We have to look at the fit range that we are using basically. So that's this part here. We have to take the continuum limit and we have to take the large N limit. Okay, and all of these errors here are really taken into account. Okay, so this was the extraction from the ground state basically. So I looked at the static potential. So are the excited states of the flux tube? Yes. It's a higher derivative operator. Now, don't ask me about the correct phrasing in the string on the string theory side. I'm unfortunately not an expert there. I think it's the TT operator. Is that correct? It's a TT deformation operator. Okay. I'm sorry. Yeah, I think so. But yeah, as I said, it's a boundary term definitely. But then I think it's a TT deformation on the boundary, as far as I know. But Michele, can you say more on this? Yeah, it's a boundary term, but yeah, I thought there was a different name to this in string theory. No, it's not a bulk. So bulk are actually all the terms with an odd power of R, and all the even powers of R are boundary terms actually. Yeah. Okay. All right. Yeah. I hope this helps. So, all right. So this extraction here was basically, as I said, from the ground state, so from the static potential. And now the question is, are excited states in agreement with that? And so what I did a test in 3-dimensional SU2 gauge theory. So extracting the excitation spectrum is actually way more difficult than just the ground state. So what I did was, for several lattice spacings, actually 3 different lattice spacings here, I just extracted the first and the second excited state with high accuracy. And then you can see that, so this yellow curve here is the result from this effective string theory, including this 1 over R to the 4 term. And you can see that in the large R limit, all these results nicely approach this curve here, the yellow curve, and they actually approach it way faster than the pure light cone spectrum or whatever. So that is really showing that the results that I get are in nice agreement with that. There seems to be a slight overshooting here, but the problem is that really controlling all of these systematics in this region becomes more complicated. So I think this is really just possibly some residual systematics here that still needs to be taken into account. One can also look at the second excited state. Actually, in the light cone spectrum, there would be two degenerate states, and now the degeneracy is lifted by these additional terms. And it might be a bit hard to see, but one can really see this lifting of the degeneracy by looking at the open and the closed symbols. And also the closed symbols approach these solid lines here, and the open symbols, these dashed lines here, and also this is really visible if one can extract the spectrum at this accuracy. And one really needs like sub-per mil accuracy, okay? So this is really a tough task doing this accurately. Okay, so far so good. So this was all in 3 dimensions. So can we do the same thing in 4 dimensions, right? But the problem is really that in 4D, everything obviously becomes more expensive. So first of all, we have an additional dimension, but also the error reduction algorithms don't work as well. So this is a bit unfortunate. So one really has to invest more and more to get the spectrum in 4 dimensions, and I'm currently working on this. But currently, it's fair to say that there's not sufficient accuracy for an unambiguous extraction of this boundary condition, boundary coefficient in 4D, sorry. There are some first signs that it should be non-zero, but really pinning down the value of it, that is very hard. Okay, however, what has been done so far in 4 dimensions is to obtain a large number of excited states. This has been done both for closed strings by Andreas and collaborators, and also for open strings. And I'm just showing a few results for open strings from this very recent study here, where they could actually go up to light cone spectrum values for this n here up to 14. So this is really remarkable. I mean, this has not been possible previously. The problem is that individually for these results, the accuracy is not sufficient to extract the boundary coefficient or anything like that, right? It's remarkable that you can get all these, but extracting these subleading properties is currently just not possible. However, what has been found is some energy levels that are in agreement with having massive modes on the worldsheet. Okay, so this has been first noticed by Sergei Dubovsky, Rafael Flauger, and Viktor Gorbenko. Well, Andreas also had some comments in their paper already, but they could actually pin this down that there should actually be a massive mode on the worldsheet, and they called this the worldsheet axion. And the same state also shows up here as this yellow state. Okay, that's a very nice and interesting result. However, what is happening to these worldsheet axion in 3 dimensions? Okay, in 3 dimensions, there's no such state. So the question is why? So if you just look at the associated Lagrange density for this particular worldsheet axion, you see that there is this coupling term here, which couples the worldsheet axion basically to the string degrees of freedom. And this term is just not there in 3 dimensions. Okay, it just doesn't exist. So if we have this worldsheet axion in 3 dimensions, then it's basically like a free particle on the worldsheet. Okay, it will still couple to the string degrees of freedom by having this derivative here in terms of the worldsheet metric, the induced metric on the worldsheet, but this term here will not be there. Okay, so it basically contributes like a free scalar particle on the worldsheet, and actually this contribution is reminiscent of the contribution of a possible rigidity term. Okay, so the ground state contribution of this rigidity term can be written down. This has been done by Michele and collaborators, and also by people at earlier stages, of course. And yeah, the contribution basically looks like this. So where one now has another non-universal parameter, namely this mass m here. Okay, so what is happening with this m in 3 dimensions? So we can do the same analysis again, now including this massive mode and this contribution of the massive mode. Then, of course, we have one more parameter, so we get larger error bars. That's just what will happen, right? We need to constrain more parameters, but we can still do this. And actually what we see is that B2 gets a bit smaller. That's also due to the fact that there is actually a 1 over R term coming from this massive mode contribution now. So that's to some extent expected. But we can also extract this mass here and clearly get a non-zero result for the mass. Okay, so we can again do the continuum extrapolation. The results are shown here. And now we want to do a large N extrapolation for B2. That's now very tough. So I'm not showing any result. It will anyhow have a huge error bar. But for the mass, this is possible. And the result is this black point down here. And we get a value, again, with all the error budget, which is minus 1.34 in these units. Okay, so here now controlling the higher order corrections is much harder because you anyhow have one more parameter. So I was not able to do that sufficiently. So I don't give an error for that. But the rest of the error budget is still there. I think that's a typo. Take it as a typo. I have noticed it earlier, but I think it should be positive. Yes, actually, I know it should be positive because now I'm expressing it in units of the string tension. Now it's positive. Yes, sorry for the typo. Okay, so yeah, right. So I wanted to ask what I learned from this, so that's what I just wanted to say. I would like to express this in units of the string tension because Andreas and Mike Tepper have done have basically extracted the mass in 4 dimensions of the worldsheet axion in the large N limit. And so this is the value that I get in 3 dimensions. It has a rather large error here. And this is the value that Andreas and Mike Tepper got. So there is a slight difference here, but if you take this value at face, the difference is not so huge. One also has to say that this is not continuum extrapolated, while this is continuum extrapolated, and the continuum extrapolation actually brings the mass down. Okay, so it's quite conceivable that the mass at least is similar in 3 dimensions. In 4 dimensions, and that we are really looking at a similar state here. Okay. All right, so that was basically everything that I wanted to talk about today. I just let my perspective stand here. I'm very interested in any discussion on these matters, and I'm looking forward to your questions. Yes.
Out of time, but I think a state like that were there. Andreas and Mike would see in this excited state. In 3D, when I looked at the whole flux, all excitations that is that by the
I mean, so why it shows up in this excited state, right, is because if you have this coupling term, right, it basically changes the quantum numbers, and then it corresponds to an excited state of being there, right? So you have a scalar particle, but it couples with this topological term, which gives it just a contribution with a different quantum number. Okay. No, of course, you have some higher order couplings, but higher order couplings generically would mean that they come with 1 over R to something contributions, right?
And there's a look at the range of R for string. Have you seen the excited states for this whole thing?
So for the excited states, the problem is that I don't know what the contribution exactly looks like. If someone can compute this, I can directly try to compare it for this. It is true that you don't see a massive mode contribution like this, that you see an energy splitting which has a massive mode in it. Exactly. But as I said, so if already the ground state gets a contribution by this, then of course it will not show up in just in the splittings, right? Not necessarily.
You mentioned holographic approach. There, of course, there is this extra dimension, right? And people always thought that maybe there is a kind of popping of the string bulk. But so far there was no evidence. Do you think it may have something to do with this? Basically, massive mode with string oscillating into this warp event.
I don't know, as I said. So I'm not really from this part of the field. So it's hard for me to say anything about this. But okay, yeah, I don't know. It could be. Just don't have any.
Found that in the excited state, you would know quantum numbers, you would know if it's like very even.
The massive mode, you mean now? Yeah, so I think it's just a scalar. So it's then it's really parity even. No, of course not. But I mean,
Scalar, it's like a linear dilator. Then it exists on the
Mhm.
Then even for one thing, you could imagine that there's a massive particle that leaves on the boundary. It's only there for both things. But this is not the boundary. This is the system. So this having energy from the boundary. Yeah, because when the from a capital point of view, how long do you think, I mean, it would take, I mean, to increase statistics, I mean, to, let's say, verify whether it's accurate or the
You mean in my case, like to pin down the or bring down the error bar? It's tough. I mean, I think so. If you want to go to the large n limit, right, you also need to go larger n. And then you need to do a continuum limit for all of those. Of course, one could go like for one lattice spacing, say, and try to do it there. That would be easier. But already now it's not well, a cheap study, let's say it like this. So it evolved over time, got more expensive. No, not necessarily. I mean, it's just, I just wanted to know whether there is a massive mode or not, right? And that was my first goal. And then I found that actually I find a mass which is similar to the one in 4D. But of course, I mean, 3D and 4D is just not the same theory. So of course you can say if there is a non-universal parameter, why should it assume the same value? And I'm not saying that it has to, I'm just finding it that the mass is similar. If I extract the mass like this, and yeah.
The ground state, so you extract this mass, taking out that energy to mass, but one can also say that the universal one of after 7 pairs. So can you distinguish whether the data prefers?
So if I include this, actually, I get agreement to way smaller values of R than if I leave it out and try just to fit with an additional 1 over R to 7. So in that sense, the data shows better agreement with it. But yeah, I mean, it's a tough task, right? I mean, you just have to, you can just compare like for different values of R, like how long can I describe my data when I go to smaller and smaller R's? And this is what makes it so hard to make any definite statement, whether this is now a contribution like this, or whether it's in 1 over R to 7 term. It could also be a mixture of 1 over R to 6, R to 7 terms, and higher order terms that just mimic this, right? I mean, you never know. You can try to do what you can, and then you can make statements. And
case strings, where one expects to find bound state,
one
sees them very clearly in the spectrum. Cited state. So there is no conspiracy there that it doesn't show the spectrum state. Okay, I think to thank Bastian again.
Thanks. I mean, all fair statements. How should you know?